Hello, my name is Mrs. Chiverton. I'm one of the science directors, and this is lesson 5 in the quantitative chemistry series. Before we start, can you just make sure that you are studying higher, combined or triple science, because this is only applicable to those particular topics. You will also need to switch off any notifications on any devices that you are using. In addition, you should have your exercise book or a pen and some paper in order to work through, and a pencil and a ruler would also be useful. You need a calculator in order to complete any of the calculations that we are doing. If you don't have one, then your phone or your computer probably will have a calculator function on it, and just pause the video in order to use that if you have to. Final thing you should have out is your outward planner, and if you look on page 147 you will find a copy of the periodic table, which you will need to look up atomic masses for certain elements. So a pre-starter just to get you thinking and about some of the activities that we've been doing recently. So we have got an equation there with some elements labelled A, B and X. They are not chemical symbols for elements, they are just representing elements. And there are 3 questions for you to answer about them. So first of all, looking at that equation, what state are the reactants in? Please could you sketch the particle diagram of the arrangement of the state for that particular example? And then finally, if you had 0.5 moles of A, how many moles of X would actually be formed? And all that information, the clues for which, can be found in the equation. So 1 minute 30, off you go. Okay, hopefully you've managed to answer all 3 of those questions. Let's just do a little bit of self-assessment on those. So, looking at that equation, we can see that element A in the reactants and element B, and then we have element X in the products. So when we look at the state symbols, we have them all with a little g after them, which tells us that each one of them is actually a gas. Then when we think about gases, we know that the particles are moving randomly and not touching. So we should have a diagram that looks something like this. There should be no pattern to it. And then finally, when we look at the molar ratios, so 0.5 moles of A would give 1 mole of X, because it's a 1 to 2 to 2 ratio, looking at those big balancing numbers as we learned in a previous lesson. So hopefully you've managed to get all of those correct. So today's lesson, we're going to be looking at calculating volumes of gases. So this is lesson 5 in the series of quantitative chemistry lessons. So our challenge today is to calculate the volume of gas at room temperature and pressure from its mass and its relative formula mass. And then our aspire is to explain how to calculate volumes of gaseous reactants and products from a balanced equation and a given volume of a gaseous reactant or product. So, first of all, I'm going to show you some pictures of some balloons, and I want you to put them in order of which has the largest volume to the smallest volume. Okay, and what I would like you to do is to explain your reasoning behind that. So there are our balloons, and I'm going to give you 1 minute to decide between the yellow, the purple and the green balloon, which is the largest volume down to which is the smallest volume. And I need you to explain your reasoning behind your answer. Okay, that's your minute up, so hopefully you've got your order and you've got your reasoning. But unfortunately, I'm actually going to have to confess that it was a little bit of a trick question. In reality, those 3 volumes are exactly the same. So 24,000 centimetres cubed is exactly the same as 24 decimetres cubed, which is exactly the same as 24 litres. They are the same volume, but just simply with different units attached to them. And the one that we are going to be using for the next few lessons is decimetres cubed. So we need to know the relationship. 1,000 centimetres cubed is the equivalent to 1 decimetre cubed, which is the equivalent to 1 litre. So you need to be able to move between those in order to address any questions. Usually in the questions they would give you volumes in decimetres cubed, but sometimes they would give you it in centimetres cubed, and you have to be able to convert between the two. So when we look at these, again, we're comparing the balloons, all right? And when we compare, we're looking for similarities and differences. So our yellow balloon has got 1 mole of hydrogen, and it's 24 decimetres cubed and has a mass of 2 grams. Look for the equivalent information for the purple balloon and for the green balloon. And what I want you to do is look for the similarities between the balloons and the differences between the balloons. So, very simple task, 1 minute 30, off you go. Okay, that's your minute and a half up. Looking then at our similarities and differences, hopefully you will have seen very clearly those similarities and differences. So the first one, the similarities, we had the same volume of gas. There was 24 decimetres cubed in each of those balloons. Another similarity was that they had the same number of moles of gas. So each of those balloons contained 1 mole of that specific gas. The differences is obviously that they contain different gases. We had hydrogen, oxygen and carbon dioxide there. And the other difference was that they had different masses. So even though it was the same volume of gas, it ended up with different masses. And this leads us on to an idea of molar gas volume. So equal amounts in moles of gases will always occupy the same volume under the same conditions of temperature and pressure. So for GCSE, what we need to be concerned about is the volume of 1 mole of any gas at room temperature and pressure, which is 20 degrees C, and 1 atmosphere pressure is 24 decimeters cubed. So we have an equation that simplifies that relationship down. The volume in decimeters cubed is equal to 24 times by the number of moles of gas that you have present. And this is one of those equations you are going to have to learn. They will not give it to you in the exams. They will expect you to recall that equation. So you need to record that in your exercise book and highlight it to know that you need to learn that equation. So it's one of those ones that you absolutely have to remember. And the other thing is that you must have that volume in decimeters cubed. Remember from previously, we said that 1,000 centimeters cubed equals 1 decimeter cubed. So therefore, to convert any volumes in centimeters cubed to decimeters cubed, we simply divide the volume in centimeters cubed by 1,000. Again, you might want to make a note of that conversion so that you remember how to do it for future questions. So, in terms of the general rule, if we have 1 mole of gas, it will occupy 24 decimeters cubed. If we double the number of moles to 2 moles, it simply doubles the volume. 2 times 24 comes out as 48 decimeters cubed. If we have 3 moles of the gas, it will be simply 3 times 24, which would give us 72 decimeters cubed. So we can literally work out from that any volumes of gas if we know the moles. So there's our summary. The total volume equals the number of moles times by the volume of 1 mole. And at GCSE, because we're doing it all at atmospheric pressure and room temperature, that translates to the total volume equals the number of moles times by 24. So we can calculate that. So here's some examples for you to have a go at. In each case, you are calculating the volume of the following gases. The first 2 questions are straightforward. You're just going to pop your numbers from your equation and from the question together to work out the calculation. Number 3 is a bit of stretch and challenge because I've actually given you the mass of the methane used there, and you of course will need to convert that first of all to moles before you can actually substitute that value into the equation to do with volume. So 2 minutes to complete those activities. Let's see how you've got on. So the first one, the volume is equal to 0.5 from the question times by the 24, which is our standard volume for 1 mole of gas. So it comes out as 12 decimeters cubed. For our second question, the volume is 15 from the question times by that 24, so it comes out as 360 decimeters cubed. Number 3, as I said, had an extra step in. First of all, we had to use mass equals mR times moles in order to work out how many moles that mass of methane actually is. So we had 4.8 from the question, our mass, times 16, which is the molecular mass of methane, 12 plus 4 lots of 1, and then we multiply that by the moles. When we simplify that down by dividing by 16 on both sides, we end up with an answer of 0.3 moles. We then go back to our other equation, where the volume equals the moles times 24. We substitute in our moles that we've calculated, 0.3 times by 24, and it comes out as 7.2 decimeters cubed. This is one of those situations where it is really, really important to show your working out. If, for example, you had incorrectly worked out the molecular mass, but you'd shown your working out, you would still get some marks for working out the number of moles. If you had inaccurately worked out the number of moles, but you still put that value into the volume equals moles times 24, you would have still got some credit for that, even though the answer would have been completely wrong. So just make sure you're absolutely showing every step of your working out. So looking back at our learning outcomes for this lesson, we can now calculate the volume of a gas at room temperature and pressure. And what we're going to do is look at how we do that from its mass and relative formula mass. And then we're also going to move on to our Aspire learning outcome. So what if you are asked to find the number of moles instead of the total volume? So in this case, you would be given a volume and we know what the volume of 1 mole is actually. So we can still substitute into the same equation. We would need to rearrange it eventually, but we write out the equation first as it is. We substitute in the numbers that we already have, and then we look at rearranging by doing the same operation on each side. So dividing the same or multiplying the same. So in this example, we have the total volume equals the number of moles times by the volume of 1 mole, and in GCSE it's at room temperature and pressure, so we know that final value is 24. So if we want to calculate the number of moles of hydrogen in 2.4 decimeters cubed, we simply write out the equation, substituting in the numbers. So our 2.4 is our volume, moles is what we're trying to find, and then we're multiplying it by 24. We want moles on their own, so we simply divide both sides by 24, and that will give us a value of 0.1 mole equaling the moles. For number 2, we can do the same thing. What is the volume of gas from 3.62 grams of oxygen? Now in this situation, we know the mass of it, so we're going to need to work out the number of moles first. So what we do there is we go back to mass equals mR times moles. We put in our 3.62, that's our mass from our question. We put in 32 for the molecular mass of oxygen gas, O2, and that's times by the number of moles, but we want moles on their own. So we simply work out those things divided by 32, and that gives us a molar quantity of 0.113 mole. We then go back to our volume equation and we substitute that in. So our volume is 0.113 times 24. So therefore it comes out as 2.71 decimeters cubed. And then finally, number 3, this was another tricky question here. So you need to be aware that sometimes they will give you volumes in centimeters cubed and they will expect you to convert that into decimeters cubed. Now, if you forget and work it out with centimeters cubed, you will get the wrong answer. But if you've shown you're working out, you will get some credit for that answer. If you haven't shown you're working out, then you may not get credit for that answer. So again, first thing we've got to do is we've got to do a conversion. We've got to turn that into decimeters cubed. And I do that by dividing by 1,000. And it comes out as 0.2 decimeters cubed. So then we substitute those into our equation. Our 0.2 is the moles times 24. We divide both sides by 24 to get the moles alone, and it comes out as 0.00833 moles. If we are asked to turn that into standard form, which they do occasionally do on these questions to add the maths values to it, then it would come out as 8.33 times 10 to the power of minus 3. We have moved the numbers 3 places to the left, so therefore it's to the minus 3. So here's some examples for you to have a go at, and I'm going to give you 5 minutes in order to do those. We're working in both directions, so there's 3 for you to find the volume, and there are 3 for you to find the number of moles, and there's an extension one in there where I'm giving you the mass and asking you to work out, I'm giving you a volume and I'm asking you to work out a mass. So 5 minutes to get as many of those done as you can. Okay, grab yourself a red pen and you'll be able to self-assess what you've done. Again, make sure that you're checking that you've got all of the working out shown. Okay, let's check those answers off, making sure that you have included all your working out. So 4 moles of oxygen, we substitute into our equation, volume equals 24 times by the moles. So that gives us 24 times 4, which comes out as 96 decimeters cubed. Equally straightforward for number 2. Substitute the numbers in, 24 times 0.25 comes out as 6 decimeters cubed. For number 3, there is an extra stage in the calculation because we've been given a mass, not the number of moles. So we have to go back to our old favourite, mass equals mR times moles, to calculate the number of moles. Once we've done that, giving us a value of 0.375, then what we need to do is substitute that into our volume equation. And so we have 24 times 0.375, and that comes out as 9 decimeters cubed. And again, as I've said before, it is really important that you show how you have worked out that number of moles, because if you've done that incorrectly, but you've then used that in the correct volume equals 24 times moles equation, then you will still get some credit marks for that on the exam. Moving over to the other side, so again, we're still using the same equation, we're still substituting in what we know. We need moles on its own, so we divide both sides by 24. And in this situation, it becomes 48 divided by 24. The 48 came from the question, the 24 from the equation, and that gives us 2 moles. Simple and straightforward for the hydrogen. So again, we simply write out our equation, substitute in what we already know. We rearrange by dividing both sides by 24, and that gives us a final value of 0.05 moles. For number 3, hopefully you spotted the change in units there. It's 360 centimetres cubed. So therefore, our first thing that we have to do, although we're going to use this equation, we have to make that conversion first. So that middle step there, 360 divided by 1,000, gives us 0.36 decimetres cubed. That is the value we put in for our volume. And then again, we do the same thing. We simplify by dividing both sides by 24, and that should give us an answer of 0.015 moles. Make sure that you've got all of those model answers down. If you were brave enough to move on to the extension activity, and you had plenty of time to do that in your 5 minutes, I'll put the answers up for that one in a second. So here was our extension, and it asked you to find the mass of 7.2 decimeters cubed of ammonia, and it does give you the clue that it's measured at room temperature and pressure. That gives you the clue that we're going to be using that volume equation. So first of all, we have our volume equals 24 times moles. We put in what we do know, our volume and our number 24. And then we divide both sides by 24, and that gives us our number of moles. And in this situation, the moles is 0.3 mole. We then go back to our mass equals mR times mole, and we substitute in our values again. So the mass is what we're trying to calculate. 17 is the molecular mass of ammonia, so that's 14 plus 3 lots of 1 for the hydrogen. And we multiply those together and we come out with a final answer of 5.1 grams. Well done to any of you who managed to get that one done and correct. Starting from a balanced equation, you can also work out the volume of gaseous reactants and products if you know the volume of one of them. So looking at this equation, we have methane reacting with oxygen to produce carbon dioxide and water. Very, very common combustion equation. What does this actually tell us about the number of moles of each substance? So this is a recall from a previous lesson. What we should know by looking at those numbers that are used to balance the equation is that the ratio always stays the same. So 1 mole of methane is going to react with 2 moles of oxygen, and they will then produce 1 mole of carbon dioxide and 2 moles of water. Looking at those balancing numbers. This is a typical example of an exam question. A student wanted to investigate the effects of global warming. The equation for the reaction was methane plus oxygen turns into carbon dioxide plus water. The volume of 1 mole of any gas at room temperature and pressure is 24 decimeters cubed. Calculate the volume of carbon dioxide produced when the students burned 25 decimeters cubed of methane. So when we're calculating, remember we're working out a number, we are expected to use a calculator to do any calculations, and we need to show our working out. We're looking at the volume of carbon dioxide. So that clues us in that we are looking at this equation, volume equals moles times 24. We have a value already. Now I find this grid method to work out calculations like this extremely easy. So I've got the three things that I am going to be calculating from my equation. So volume of 1 mole and moles. I've got my two chemicals, methane and carbon dioxide, that are mentioned in the question. And I've put in already the numbers that I know about. So the volume of the methane is 25 decimeters cubed. I got that from the question. The volume of 1 mole is always 24 when it is at room temperature and pressure. So I've put that in for both the methane and for the carbon dioxide. I then can use my equation to work out the number of moles of methane because I have two pieces of information to calculate the third. So it becomes 25, my volume, divided by 24, and it comes out as 1.042 moles. Now I have to look at the equation, and it's 1 mole of methane turning into 1 mole of carbon dioxide. I know that from the balancing numbers in the equation, so therefore it's a 1-to-1 ratio. That means that the moles of carbon dioxide are also equal to 1.042. Therefore, if I go back to my equation, volume equals moles times 24, I can substitute those numbers back in, and I find that I actually make 25 decimeters cubed of carbon dioxide as well. So this is a typical example of an exam question for you to have a go at. The student wants to make 11 decimeters cubed of ammonia. You've got the equation there, nitrogen plus hydrogen making ammonia, and you've got the balancing numbers in there. It's reminding you that the volume of 1 mole of gas at any room temperature and pressure is 24 decimeters cubed. This is what you need to do. Calculate the volume of nitrogen that the student should react with hydrogen to make 11 decimeters cubed of ammonia. And it's asking you to give your answer to 3 significant figures. And I'm going to give you 2 minutes to complete that. Okay, we're going to go through that one in a second. So question 1, we were looking for the amount of the volume of nitrogen that would be needed to react with hydrogen. So Again, we use the grid system, so we write down on the left-hand side the things from the equation. So we know volume of 1 mole, and moles. We put in the volumes and the quantities that we already know. So that ammonia we know is 11 decimeters cubed from the question. The volume of 1 mole is 24 because it's done at room temperature and pressure. So that allows us to work out the number of moles of ammonia. So in this case, it's 11 divided by 24 comes out as 0.4583 moles. We don't round that number up at this point. Leave it as whatever big number comes up on your calculator. We then look at the ratio, and it is a 2-to-1 ratio, 2 moles of ammonia for every 1 mole of nitrogen that is used. We get that from the balancing numbers in the equation. So that means that if it's a 2-to-1 ratio, we need to halve the amount of moles of nitrogen. We divide it by 2. And again, we write down the number that we've got from our calculator. So you should have got 0.22915. We can then use that and the 24, which is the volume of 1 mole, back into our original equation, and we end up with 5.4996. Now remember, we were doing that to 3 significant figures, so we round it to 5.50. It is perfectly acceptable to use this grid method when you're working things out in the exams. It keeps things organised and it shows the examiner the processes that you are going through. If you aren't using the grid method, you need to be careful that you are clearly labelling what your quantities are and what your calculations are that you are doing them. So question 2, very, very similar. They're wanting to investigate those effects of global warming. This time we're asking the volume of carbon dioxide produced when 100 decimeters cubed of methane is burnt. Off you go. Again, you can use the grid method for this to work your way through logically what the calculations would be. So this is another way of setting it out without using the grid system. Volume equals moles times 24. So the moles of methane is 100 equals the moles times 24. We simplify that down and by dividing both sides by 24, and we end up with the number of moles being 4.167 moles. Then in a separate column, we know that the ratio of methane to carbon dioxide is 1.1, and I've actually said that very, very clearly. So that tells us that the moles of carbon dioxide is also 4.167. We write down our equation again, we substitute in the numbers that we know, and we come up with our final calculation. And again, it's logically set out, it's signposted and labelled all of the way. So again, check your answer and make sure you've got the correct answer and the correct working out. Add on anything that you think you have missed. So really, we have now addressed that last one, explaining how to calculate volumes of gaseous reactants and products from a balanced equation and a given volume of a gaseous reactant or product. So this is an example of an exam-style question. So it says, airbags are used to protect the passengers in a car accident. When the crash sensor detects an impact, it causes a mixture of chemicals to be heated to a high temperature. Reactions take place between nitrogen gas and the nitrogen fills the airbag. So we've got an example before the crash and after the crash. The mixture of chemicals contains sodium azide, which decomposes on heating to form sodium and nitrogen. And we have got a balanced equation for that. And we're also told that a typical airbag contains 130 kilograms of sodium azide. Now, I wouldn't have expected you to know sodium azide at all. However, we've got that information there, so therefore we can use the calculations. So first of all, you've got to calculate the mass of nitrogen that will be produced when 130 grams of sodium azide decomposes. And we've got some atomic masses there. And we've also got the second part to the question, about 1 gram of nitrogen has a volume of 0.86 litres at room temperature and pressure. What volume of nitrogen would be produced from 130 grams of sodium azide? And it gives you a value to use if you weren't able to do the first part of the question. So I'm going to set you off on that, and I'm going to give you, again, 2 minutes in order to do that. If you can't read it, the formula for sodium azide is NaN3. NaN3. Right, let's work our way through that. So first of all, you had to work out the molecular mass of sodium azide. So that was 23 plus 3 lots of 14, which came out as 65. And there was actually 1 mark for doing that. So if nothing else, when we get these complex things, if you work out the molecular mass of something, you may get a mark. We then had to use mass equals mR times moles. So we had 130, which was the mass from the question, 65 from the molecular mass we've worked out, and simplifying that down, we find out that we had 2 moles. That was also worth a mark. We then looked at the ratio, which was 2 to 3 from the equation. So therefore, the moles of nitrogen is 3 moles if we had 2 moles of the original one. So then we go back to mass equals mR times mole, and we can work out that the mass there is 84 grams. And then for the second part, that's where our volume of the gas is equal to the moles times by 24. So again, we substitute in 3 times 24, and it comes out as 72 decimeters cubed. All the same kind of calculations we were doing It's just based on an exam question. And it doesn't matter if you didn't know what the chemical was, because they've given you the formula. So, in terms of our key learning points, if you have missed any of this information, please add it to the notes in your book. So, equal volumes amounts in moles of gases occupy the same volume under the same conditions of temperature and pressure. The volume of 1 mole of any gas at room temperature and pressure, 20 degrees C, and 1 atmospheric pressure is 24. The volume in decimeters cubed is always equal to 24 times by the moles, and the volume must always be in decimeters cubed. There are 1,000 centimeters cubed in 1 decimeter cubed, so we can convert from volumes in centimeters cubed by dividing by 1,000, and that will give us our volume in centimeters cubed. So the final thing for you to do today is complete the Google quiz, which will be automatically marked for you, but make sure that you've got pen, paper and a calculator ready still, because you will need to do a lot of working out. Good luck.